Ladies and gentlemen, it's 3 p.m. of the Central European summertime, and it's my pleasure to welcome you on behalf of the International Society of Photogrammetry and Remote Sensing to the second presentation of the Keynote speaker series, which we have launched this spring due to changes in our life, and not only ours, but also ISPRS life. And the second presentation will be given by Professor Clifty. He's Professor of Geomatics Engineering at the University of Calgary, where he served as department head from 2013 to 2018. Prior to joining University of Calgary in 2008, he was with Curtin University between 1997 and 2007. Derek served as editor-in-chief of the ISPRS Journal of Photogrammetry and Remote Sensing between 2013 and 2020. Prior to that, he served 2 terms as chair of ISPRS Working Group 5-3, Commission 5, Working Group 3 on terrestrial laser scanning. He is a recipient of the 2020 Schwidewski Medal. So this is my message as a Secretary General of ISPRS, and I would like to ask Derek to take over the role and start his interesting presentation.
Okay, thank you, Elena. Thank you for the very kind introduction, and hello everyone, or good morning, afternoon, or evening, wherever you are in the world. It's very much my pleasure to be here today to talk to you about some of the research that my group has been doing over the last few years. And as you can see from the long title, it's about laser scanning, specifically network design processes, new network design processes for supporting reality capture activities with terrestrial laser scanners. And I think it's worthwhile to start off just to define exactly what is meant by terrestrial laser scanning. I'm sure most people in the audience are quite familiar with it, probably more so than me, but I think it's important to have sort of a common ground for starting in terms of terminology and notation. So let's do that. So terrestrial laser scanning we can define as being a reflectorless imaging, active imaging method. And it's typically one that is mounted upon a tripod, though it doesn't have to. And it collects 3-dimensional point clouds like the one we can see in the bottom right there, the Golden Buddha statue in Bangkok. And the way it collects these data are fundamentally with range finding. So laser range finding, a pulse of light is emitted and backscattered by the object, and either the two-way flight time or the phase shift is measured to determine the distance to the object. And it collects a series of these measurements through a couple of beam deflection mechanisms. So in the first instance, there is a vertical profiling mechanism where the instrument collects data from range measurements from down below, and then the rangefinder is deflected in nominal increments of arc up through the zenith and then behind the instrument again. And then a series of these profiles are collected as the instrument rotates around its vertical axis. And there may be a number of other ancillary pieces of information that are collected by integrated sensors on board the scanner, but that's the basis of it, and that's how we will go forward. And in terms of reality capture applications, my group's been involved in a few over the years. In particular, some in digital heritage recording. So here are 2 examples from southern Alberta, where I happen to live. The one on the left, this is a glacial erratic. So this is a large quartzite boulder transported to an area south of Calgary during the last period of glaciation. Now, this might seem like a geological application, but this is a site of local significance, shall we say. So there's cultural significance to this site, to the Blackfoot Indigenous people of southern Alberta, and it is a sort of a local tourist attraction because it's a striking boulder on the prairie or steppe landscape. And there's concern from the Alberta Culture and Heritage Ministry that this site is being degraded because of lots of human activity. So we've been involved in a periodic campaign over the years to collect the laser scanner data of this large site and try and ascertain whether or not there has been change to the actual site around the big rock, as it's called, the Okotoks. On the right, what we can see is an historical aqueduct, Okay, this is not Roman era aqueduct. This is much newer. This was constructed in southern Alberta, about 200 kilometers southeast of Calgary, around about 100 years ago, to bring water to the southeast agricultural district, which is very arid but yet very fertile at the same time. It's long since been disused, but it also is a monument of local significance, and it's deteriorating quite badly, as you might be able to see from the image there. And we were involved in a campaign to try and ascertain the current state of the aqueduct by using laser scanning, then try and infer where the damage has been experienced to it, so it can be remediated accordingly. Now, this next example is one more of metrology, I would say, or dimensional control. And the problem here is this. So we have shown in the CAD model on the top left, a prefabricated pipe and flange module. So this is an assembly that would be constructed at a works yard and then shipped to a site where oil is going to be refined from the Alberta oil sands. And the purpose of this project was to determine whether or not the flanges, which you can see the couplings that match the two pipes together, the flanges are in the correct place, meaning when this prefabricated module is shipped to site, will it actually fit to the existing infrastructure? Because if it doesn't, then that requires a rework. It requires cutting and welding and so forth. And they would rather do that in the fabrication yard than on site, which is current practice. And so they want to scan this prefabricated module in the works yard and then determine dimensional compliance. And so that means collecting the point cloud on the top right, which is really a jumble, locating each of the flanges, basically the point cloud around the region, and then performing some identification processes to determine the front face of the flange, so the plane, and then the cylinder. We can intersect the end axis of the cylinder with the flange and get the position. And once we have this for all of the flanges, then we can make that decision whether or not the assembly is dimensionally compliant. And then finally, this is an application that's actually long since, it's actually completed from our end. It's commercialized and the technology has been transferred, but I think it's relevant to mention in the context of what I'm going to talk about for this presentation, which we'll come to next. So this is a comminution mill on the left-hand side, this big steel drum. And basically it takes big pieces of ore in one end, and the drum rotates, the ore falls on itself, steel balls fall on it, and out comes a powder. Mixed with water, it becomes a slurry, and then it goes on for more chemical processing in order to liberate the mineral from the ore, and that might be aluminum or gold or uranium, whatever. Now, as you can imagine, pieces of rock spinning around, it's a very harsh environment, and the inside of this the liners of the mill wear out over time, and that can be catastrophic if one breaks, but also it can compromise performance in terms of the throughput of the mill. And so our idea was put a laser scanner in there during the planned downtimes and collect laser scanner data like we see in the center, the point cloud, and then correlate that with the plans of the mill. And that gives the milling engineer a very good picture as to what the thickness of the liner is at every point that can be seen inside the mill. And so we get this thickness map on the right-hand side for part of the mill, where blue is very thick and orange and red are thin. So for all of these examples, we have fundamentally some sort of question that needs to be asked or answered. It is asked, but we need to answer it. So what is the thickness of the liner inside the mill? Are the flanges in the correct place? Is the heritage structure experiencing some sort of, is it damaged? And to be able to answer that question, we might go through a process with the terrestrial laser scanning that looks like this flow chart in the center. Now it's a sort of high level, and there are many sub-processes perhaps that are encapsulated within these blocks, but I think it's sufficient to describe the process. So there's some sort of data collection that's necessary, obviously. And then if we have to utilize multiple instrument locations because the object is large and complex, like the pipe and flange module. Then there's some sort of registration process that needs to be performed. And then finally, the modeling process. That's where the intelligence really lies, because this is how we're going to interpret the data in order to answer that question. And all along the way on the left, we have quality assurance measures, okay, to help us ensure that we achieve the data quality we want. And then we have quality control measures on the right to, basically test whether or not we actually did achieve the data quality. And so what I want to talk about today are two of those quality assurance processes, specifically one related to network design, the configuration problem. And then the bottom one is about calibration, but it's actually related to the first order design. So it is a network design problem at the same time. So those are the two subjects I want to talk about in terms of the quality assurance for terrestrial laser scanning and 3D reality capture. So this is called, called TLS viewpoint planning. My mouse is a little overactive, sorry. Okay, so this is a network design problem, and fundamentally network design can be stated as this. Give us a network, or design a network, a configuration, given a certain measurement volume that we must cover, and a number of criteria, and those might be precision, reliability, as well as economic or cost criteria. And if we look at the history of network design development in terms of methodology, it really started, in my view anyway, in the 1970s with the design of geodetic networks. And then that continued, and then in the early 1980s, we saw a lot of work being done in close-range photogrammetric network design. And now we're at the point of terrestrial laser scanner network design, which is an active area of research still. And there are many considerations that we have to take into account, such as the coverage of each of the scans, the number of scans, the number of targets necessary, the scanning geometry, as well as the overlap. And there are others that we can consider as well. And so if we look at this in a little more detail, we can break down network design into 4 problems. And this is what Professor Pharaoh did almost 50 years ago now, where network design was decomposed into zero order design, which is the datum problem. The first order design, which is configuration. That's what we'll talk about here today. Weighting and densification. And these processes still certainly hold up today, are still very relevant. So let's look at the TLS first order design. And basically, we can boil it down to 2 sort of tasks that must be performed in this first order design. First is the number and configuration of viewpoints or instrument locations required for complete coverage of a site, and with the desired data quality, as we talked about, precision and reliability. And we can see on the left-hand side the example of an electrical substation where the objective was to produce a 3-dimensional CAD model of the as-built condition of that site. And you can see the viewpoints indicated by those. There are 7 actually black circles. A few of them are easier to see. And those are basically the shadows beneath the instrument the data holds. And they're surrounded by this green ring, if you will. And so the point cloud is colored according to laser and return laser intensity. That's why they have that color. The other aspect is the number and configuration of targets required for scan registration. And I'll acknowledge that this is not the only way of registration that we can perform with laser scanner data. There's, of course, ICP type methods, but there is certainly need in many instances to still utilize targets. That's why I mentioned it. And for both of these processes, what we would like is to minimize the number of viewpoints and the number of targets, because that reduces the labor requirements for the field data collection, as well as for the post-processing. What we'll focus on in this part of the talk is the one on the left, the viewpoints, so the number of configurations, viewpoint configuration. And if we look at the literature on this subject, it's quite diverse, actually, and this slide can't necessarily do it complete justice, but I think at a high level it encapsulates the 2 main approaches, which, at least the way we've considered to classify them. And the first approach to designing the viewpoint location is called we can call them the next best view or next best scan methods. And here we can envision is a say like a a robotic vehicle moving through an environment and mapping it as it goes. And when it constructs a map with the laser scanner, then it's going to make a decision. Where should it go next? Where is the next viewpoint? Okay. And this is a natural sort of way in which to perform this process. But the problem from our perspective in applying this to terrestrial laser scanning is that each subsequent view is biased based upon the previous placements. Okay, so in the greedy algorithm, then, which was developed by Sylvie Sudarissanane and Roderick Lindenberg, they took more of a holistic approach, I suppose, from the terrestrial laser scanning point of view, where they decomposed the candidate environment into a number of discrete entities and then performed some visibility and occlusion analysis to decide upon the best viewpoint locations. Now, one thing that's common to both these methods is that the analyses are based upon the entire workspace at the same time. And early in our work in this area, we looked at a number of heuristic optimization methods to try and solve this problem in a better way if we could, like particle swarm optimization, simulated annealing. And what we found is that there are a lot of empirical parameters to tune and lots of computations. And so the path we ended up going down was to try and build upon, excuse me, the greedy algorithm, where we have a hierarchical process and something called the weighted greedy algorithm. That's what I'll describe next. And I should mention at this stage that this was the PhD work of one of my former students who's now a postdoc in my group, Fengman Jia. So let's look at the original greedy algorithm, then we'll see what the weighted development is. So what we have on the top left is a little cartoon showing a hypothetical environment, trapezoidal room or corridor, whatever it may be. And it's been decomposed into 10 wall segments, S1 to S10. And the workspace environment has been, we've delineated 7 candidate viewpoint locations. So there are 7 possible instrument locations. We need to decide upon a network configuration with a minimum number of viewpoints so as to cover all 10 wall segments. And so what we do is construct the visibility score table. So for each viewpoint, VP, we enter a 1 or a 0 for each of the wall segments, depending on whether it's visible or not. So S1 is visible for VP1, S3 is not. The shading indicates which wall segments are visible from a particular viewpoint candidate, depending upon range, incidence angle constraints, and whatever other criteria we want to utilize. And so the visibility score is the summation along any one of those rows. The greedy aspect is we include the viewpoint with the highest visibility score in the network. All right. Now, as you can see, there are many that have the highest score, so we arbitrarily select number 1. Let's do that. And what we do, so that means viewpoint 1 is included in the network design, and then we have to reanalyze the remaining environment, excluding those segments that it can see, and we come up with what is the next highest visibility score. And there are several, so we select viewpoint number 3. And then we follow the same procedure. So we eliminate the wall segments that are seen from that viewpoint, and then we perform the analysis again. And we do this until basically all the wall segments have been covered, and that's our final network design in terms of viewpoints. Now, what we've tried to do is, well, we've recognized that this doesn't necessarily consider priority amongst viewpoints. So maybe there are some that are more important than others, and I'll explain why. So first of all, though, let's take our visibility score table and compute the sums along each column, so the visibility count. And we use those to normalize the entries in the visibility score table. And what that does is it places priority to certain viewpoints, because you can see that some walls can only be covered from one particular viewpoint. And so therefore, perhaps that viewpoint should have higher priority because it's more important to covering the full environment. And so then we sum up all those normalized scores as the visibility weight. And the viewpoint with the highest visibility weight gets included in the network configuration. So you can see there are again a couple. So we'll select number 4. And then we perform basically the same process as just described. So we viewpoint 4 is included in the network, and we exclude those wall segments and exclude it from the subsequent analysis where we determine what viewpoint should be added next. And that's number 7 because it has the highest visibility weight. And again, this process continues. So we get a slightly different picture in terms of the network design. Now, if we look at a little more realistic environment, this is a building on our campus, or part of a building on our campus. It's a 80 by 80 sort of capital gamma letter shape. And what we've done is decompose the outside of the exterior of the building, the space surrounding the exterior of the building, into a very fine grid. And each grid intersection represents a candidate viewpoint. And so we want to decide where should the viewpoints be placed? Where should the scanner be placed to give us complete coverage of that building? And we have the heat maps showing the solution, or showing candidate sort of scores from the weighted greedy algorithm and the original. And we cannot directly compare the scores in these heat maps because one is non-integer and the other is integer, but we can compare the patterns. So yellow in both cases means higher priority. And you can see that the weighted greedy algorithm gives us a completely different picture in many areas. So it prioritizes certain viewpoints quite differently. What we also notice, though, is that at this higher fine resolution detail, that there's a lot of points to analyze, lots of computations. So we have very fine resolution. And as we increase that resolution, so as the sampling interval in that grid of candidate viewpoints decreases, the number of computations increases, basically in proportion to the square of the number of samples. So the next idea we had was to try and adapt the resolution where necessary to reduce those number of computations. All right, so to do that, we make a couple of assumptions. First of all, the weighted greedy algorithm will give us very similar solutions at different resolutions. So we've computed the weighted greedy algorithm candidates for sampling resolutions of 10, 5, and 2.5 meters. And the one on the left is a little more difficult to analyze, perhaps because of the coarseness, but on the middle and the right, I think you can see that the patterns in terms of the colors of the heat map are very similar. So they're similar type of solutions, even though the resolution is different, and we again can't directly compare the scores. And the second assumption is that we can select viewpoints hierarchically. So we can start at a very coarse resolution, like on the left, and then in areas where we selected viewpoints that are very close together, we can analyze those areas in more detail. So if they're close within a certain threshold, and analyze those areas in more details at the next level of resolution. So we don't have to repeat the analysis at the finer levels of resolution. Only where it's necessary do we do that, meaning where necessary, meaning where two candidate viewpoints are close. So that's the strategy that we've come up with. So we first generate a set of candidate viewpoints at coarse resolution over the entire workspace. Then we use the weighted greedy algorithm to come up with a set of optimal viewpoints, supposed to be optimal viewpoints. And then we analyze each pair of viewpoints, and we regard them as either being distinct or distinguishable, so they're separated by a certain distance, or indistinct or indistinguishable, meaning that they're in close proximity to each other. And these, under the assumption that redundant viewpoints, so this is almost like third order design, redundant viewpoints are close together. So we can densify the analyses in the vicinity of those indistinguishable viewpoints. So let us look at an example. So this is the McEwen Student Center. It's a multi-use building on the University of Calgary campus. There's a lot of restaurant space, fast food restaurant, unfortunately, commercial space, as well as some administrative space. It has a number of occlusions within the environment, in particular stairwells and elevators or lifts. And it has this area in the center called we call it restricted area. Well, this is basically the seating for the food court area. And we regard that as as being transparent. So we could set up the instrument and scan through it and see the walls, but we can't set up in that area. So viewpoints can't be placed there, but we can see through it. Okay, so next we'll show you here are the solutions from the original and the weighted greedy algorithm for viewpoint placement. What we can see is that the weighted method gives us 4 fewer, so in 24 instead of 28, which does represent certainly a savings. Interestingly, the configurations are quite different in some locations. And what we can also see for the weighted approach is we have these dashed circles around each one. So the circle has a radius equal to the resolution of our hierarchical strategy at which that viewpoint was decided upon. And we can use that in our sensitivity analyses, because the objective of this would be to produce a plan that a field crew could use to go out and collect the necessary data of this student center building, the inside of this student center building. Right? And so the sensitivity analysis tells us how careful do they need to be in that process. So that's what we have on the left here. So within that circle that I mentioned, we generate a number of random viewpoints, so 100 different viewpoints in that location. And the color scale that we see indicates what proportion of the visible segments from the weighted greedy algorithm viewpoint are visible from each of those randomly generated locations. So it can tells us how sensitive that location is in terms of coverage. And in most locations, you can see it's everything's yellow, so it's not above 90%. So we get most of the wall segments covered. There are locations though where it is much lower. We see a bit of green and blue, especially in corners and alcoves and things like this. We can take that sensitivity analysis a little bit further with the figure on the right, where we've generated for each wall segment a color scale indicating the proportion of solutions from which the wall segment is not visible. Okay, so this is the invisibility count. So in most cases, you will see the wall segments do not have any colored dots on them. And that means that the invisibility count is 0. So 100% of the random solutions can see that particular wall segment. But there are some locations where it's maybe like only 10% or so. All right. But what's, I suppose, more of concern are areas like this. This is a column where the invisibility count is quite high. We don't actually regard that as much of a problem because if it's a column, whether it's in square cross section or circular, we can model that quite easily. It's more the wall coverage that's of interest, I suppose. But it is something perhaps that could be improved in the future. And finally, what we can do is perform the variance propagation. So the rigorous error propagation that will accounts for all the measurement errors in the orientation process as well as the radiation process, and determine the point covariance matrix of each end of the wall segments, and then extract a precision measure from that to tell us whether or not we are actually meeting the criteria for precision for that network. Okay. So there is a bit more to this story. There's the target placement that I haven't talked about, but we have a publication about that you can go to. But what I want to do now is switch into the next topic. Okay, and this is also related to first order design, is about the observation distribution modeling. And I'm going to preface this with a few slides about instrument calibration. And I think it's fair to say that the importance of terrestrial laser scanner calibration has been recognized. And the purpose of it is excuse me, the purpose of it is to determine the systematic error model parameters of an instrument. So an instrument may not be manufactured perfectly, or over time and usage, it may become out of alignment. And what we want to do is determine the parameters that are deviations from the cartoon on the right, which is an idealized system model where all axes are mutually orthogonal where relevant, and they intersect at a common point, and there are no eccentricities, and the origins are at the points of intersection of axes, and so forth. There are many aspects to it, many facets to it that we won't go into in detail here. But to determine those error parameters, an accepted procedure is the self-calibration procedure within an indoor environment of targets. And I'll show that briefly. So there. Okay, So here is an indoor target field. The walls, the floor, and the ceiling are decorated with many of these signalized targets, a white circle on a black background. You can probably guess where the instrument locations will go in between the, well, there's the spider sort of tripod here, but in between these circles of targets on the floor. So this is the environment, and the job to do the calibration is one of setting up the instrument at different locations in that room and collecting scans for the purpose of observing those targets. Okay, so this is a top view looking at the targets and the scan locations. Then what we have to do is identify the target areas from each of the scans that are collected, and then ultimately measure the center targets. And we might do that with some sort of model-based procedure so as to find the center. And what we're after are the center coordinates there, the spherical coordinates of range and the two deflection angles. And once we have those observations from each target in each scan, we can perform a grand sort of self-calibrating adjustment to determine the calibration parameters. Okay. Now, first order design is, of course, an important factor that influences the solution quality, and this is known very well from self-calibration of cameras, where there are a number of well-known design measures that should be utilized in a network for camera calibration. One of those is that we want to try and fill the format completely with targets or with observations. And I'm going to illustrate the importance of that with a simple simulation. So this is of just determining radial lens distortions. So we have an image plane on the left with 100 randomly generated points. And the purpose here is quite simple: determine this K1 parameter for the distortion profile of the lens, the radial lens distortion profile. And in doing so, we come up with a curve on the left. So the black curve is the actual trend of the distortion, and the blue curves are the error envelope, so plus or minus K times the standard deviation. So I've exaggerated them quite a bit for display purposes. And that's determined with the full coverage of the format. In the bottom, I've reduced the coverage to only 80% of the format. What we can see is that has quite a significant impact on the precision. Basically, the precision is worse by a factor of 2. The bounds of the error envelope have doubled. All right, so 80% change in coverage gives us a factor of 2 worse precision. And that's because of the observation distribution, same number of points and everything else the same. And we find that the distribution of the observations impacts the quality in other problems as well. And I've got an example from linear regression. These are simulations again, but we've worked out the analytical relations as well. And so here the problem is quite straightforward. Determine the parameters of this line, y equals mx plus b. So we want to determine the slope m and the offset b from a set of observations y, and the x coordinates are treated as constants, right? So I've generated many observations, and there are two aspects to consider here. So the x observations have been generated more or less in a random fashion, but they are error-free. It's just their location is random according to some distribution. In this case, it's uniform sampling. It's very dense, so you can't see the spacing in between the points very well. The y observations have random errors, of course. So the top one is a uniform distribution. So the actual histogram and the distribution I generated that from are shown on the right. Down the bottom, this one is more centrally weighted, so it's sort of a triangular distribution. There are more observations clustered in the center. And then the one at the very bottom, that density near the center is even more accentuated. It's more clustered. And what we can see is that depending upon the observation distribution over that domain, x equals -1 to x equals 1, same number of observations, we can see that the precision of the line fit varies quite considerably. And in particular, it's the precision of the slope. So questions that can come from this is, first of all, how can we model the observation distribution in a least squares problem like this? And how can we use that model to determine exactly the impact of the distribution on parameter quality. And then how can we use this model to try and improve network design? These are simple problems, but we want to apply this to more complex examples eventually. Now, of course, we can't answer these questions by numerical simulation, but what I think is preferable is to use an analytical approach. So some sort of continuous function that describes the distribution model. Okay, so that allows us to do the solution, compute these answers in closed form. And here now I'll return to the example of first order design for the terrestrial laser scanner calibration. So we'll revisit this idea of observation distribution, but let's go back to the observations first. So remember, in the laser scanner calibration, we have to make the measurements of the centers of this target, each of these targets. And those observations are the spherical coordinates, range, direction, and elevation angle. Now, I'll recognize that there are different parameterizations for these observations that may depend upon the actual instrument architecture and so forth, but that's not particularly important right now. What's the main focus are these terms, the systematic error correction terms. So we want to look more deeply into those. Before we do that, though, we'll look at the distribution of the observations, just like we did for the linear regression and for the distortion estimation. So we have here the histograms of horizontal direction observations. They range from 0 to 180 degrees because the instrument collects data almost in 360-degree vertical profile, and so it only has to rotate in about its vertical axis by 180. So we have 6 different calibration data sets, actually from different target fields and different instruments over different times, so different environments. And what's common to them is, despite the raggedness of the histograms because of some limited sample size, they all are more or less uniformly distributed, meaning that we have horizontal angle observations spanning the whole domain of horizontal direction, which is, intuitively, this makes a lot of sense. This is something that's quite desirable. We have observations uniformly over a complete domain. When we look at the elevation angle observations, the story is quite different, though. Well, let's take some time to interpret this. So what we see is we have elevation angle observations clustered at the horizon. So at 0, as well as behind the instrument at 180 degrees. And then up at zenith, there are actually very few, despite best efforts to place targets up above the instrument. And so the question is then, well, what is the impact of this in our self-calibration problem? And to contextualize that, let's go back to our direction observation and look at a couple of terms from that systematic error correction, delta theta. So 2 of the most important errors are collimation axis error and the trunnion axis error. So the collimation axis error, it's an error that affects the horizontal directions. Okay, and this is because of non-orthogonality, basically, of the laser beam and the horizontal axis. It is constant at the horizon, so at 0 elevation angle. And then as the elevation angle increases, the error in the horizontal direction increases with the secant of the elevation angle. So it's more or less constant for a long time, and then it increases quite suddenly, which you can see from the graph on the left. The trunnion axis error, that's non-orthogonality between the vertical and the horizontal axes. That one is 0 at the horizon, but then grows very rapidly as a function of the tangent of the elevation angle. All right, and you can see that growth on the right-hand side. So, given what we just seen about the distribution of elevation angle observations in the previous slide, how does that impact the estimation of these important coefficients, B1 and B2? So how does the distribution of alpha influence B1 and B2's precision? So to answer that, what we can do is look at, we can study those 2 parameters independently, and we can do this as long as we have other good first order network design measures in place for the calibration network. So we have this derived observation, which is just observed direction minus the functional model from the Cartesian geometry or the spherical geometry, equal to B1 secant theta, B2 tan theta. And if we wanted to estimate B1 and B2, we would set up a system of observation equations for our n number of point observations that we have, where the columns of the design matrix A have the secant and the tangent of angle alpha, and we are trying to determine B1 and B2. And from that, we can formulate our least squares normal equations. And it's mostly this one, the normal equations matrix N, that's of interest here. And when we look inside at it, it's not that complex. We have summations from 1 to n of number of observations. On the diagonal, we have secant squared theta and tan squared theta, and then product of the two. And if the data limits are symmetric, then those terms actually just go to 0. Okay. In constructing this, we've defined a weight matrix, which is just a scalar matrix, which is very common, where we have a common variance for the horizontal direction observations. So the weight matrix is 1 over sigma squared. What we're going to do now is modify this. So this is basically squares. We're going to modify this in 2 ways. First thing is we're going to multiply the normal equations by this quantity delta alpha. So we have delta alpha equal to alpha 2 minus alpha 1. And these are just the observation limits. So the maximum, minimum and maximum values normalized by the number of observations. Okay. And then we're going to redefine our weight matrix. It still has the precision of the observations, but now in the diagonal, it has a function evaluated at each elevation angle. And this function P models the distribution of the observations, much like we saw with the linear regression. Okay, and there are conditions placed on this function to keep P from make sure it's positive definite, and these extra weights are normalized. So now when we put those into our least squares normal equations, we see that the summations have this additional weighting term, P, and we have this delta alpha term out front. Now, let's assume that we have the luxury of many, many, many observations. So we can take that practical idea into practice, into the theory by saying, well, in the limit as the number of observations approaches infinity, then these summations become integrals. And so we have the integrals of weight, the observation distribution times these functions, secant squared and tan squared. What's of most interest to us is the inverse of this matrix N, because that is the covariance matrix of parameters that tells us what is the precision of B1 and B2, the collimation and trending axis errors, these important errors. And we see that in this case, it's a function, they are a function of the variance of the observations and this weighting here. So this is how the observation distribution factors into the precision of these parameters. So means if we can model the observation distribution with a continuous function, we can predict parameter precision in closed form. So we don't have to perform any numerical simulations in our first order design. The question comes, well, how do we choose an observation distribution? Well, we can take a look at go back and to our empirical distributions, and we see that this red curve, which is a raised cosine model, it's got 2 lobes, actually fits the data reasonably well. You might argue that, well, maybe this one on the right, it fits better than some of the others, but we've evaluated this, and the raggedness doesn't really matter. It does the model fit the trend reasonably well overall, and that is true in these cases. So we can come up with a model for the observation distributions, and we can use that in our normal equations to predict parameter quality. We can always also take that further and hypothesize, well, what might be a better distribution? Whereas this is the conventional distribution, data concentrated around the horizon, a better one might be data concentrated more at the zenith, up above the instrument. Now, intuitively, this makes sense, but it's nice to see it in analytically, and then in practice, we can use that idea to guide us to a better network design. So we have two rooms here, one with the conventional target design where we have many targets on the walls and only a few on the ceiling. And then on the right, we have the improved design where most of the targets are actually on the ceiling instead of the walls. And this does improve the parameter precision. Not so much for the B1, because B1, as I mentioned, is more or less constant for a good range of elevation angles. But for B2, we can see that we can almost double the precision essentially. Now, admittedly, these numbers are small, they are in arc seconds, but what it tells us is that if we have an improved design, then we can perhaps dial back, reduce the number of targets that are necessary because we have an improved configuration. We don't need as many targets to get the precision we desire. Okay, so just looking at the time, I think it's time for me to wrap up. So what I'd like to summarize by making a few statements. And the first is that I think network design is very much still a relevant idea in photogrammetry and in geomatics, however. And hopefully the two examples I've shown here have illustrated that. So the first one is about viewpoint planning. How can we minimize the number of stations necessary to cover a complex environment? And the second one is the particular application was self-calibration, but really the bigger picture is how do we optimize the distribution of observations in order to maximize precision. And as I just said, this calibration example is just one possibility. There's lots more applications, I think, that can be made of this technique. So there's much more work for me and my group to do. So to finish up then, I'd like to acknowledge some people. So Professor Lena Alunova, who invited me very kindly to give this presentation, and then some members of my group, including Fengman Jia, whose PhD work, as mentioned, was the viewpoint planning, and then some former and current students, as well as collaborators, funding sources for me and some of my students. And with that, I'll end and leave you with a picture of scanning in the Canadian Arctic a few years ago. So thank you very much, folks. I hope you've enjoyed it. And yes, I guess time for questions.
Derek, I must thank you very much. It was very interesting, even though for me, I am not a specialist in laser scanning, but still I was amazed by lots of work you have involved in your work and research with your students and colleagues. And I would like to read the first question, which I found in the QA part from Mahmoud Rizawad Delavar, and he thanks you for your very informative webinar. Could you explain what would be the threshold for precision and accuracy of TLS network design, and how error propagation will affect the optimum network design in your WGN and ordinary network design? With best wishes, Mahmoud.
Okay, so there are a few questions there. So, well,
the first one would be the threshold for precision and accuracy of TLS network design.
Well, I would say that's really dependent upon the application. It depends what is required for a particular project. And so, for example, from the heritage recording, the precision and accuracy requirements are relatively low compared to the dimensional control of the flange and pipe work. So for the aqueduct, for example, we were looking for a few centimeters essentially. It wasn't rigidly defined, but really I think the best answer I can give is that it's very much project dependent.
And the following one, and how error propagation will affect the optimum network design in your WGN and ordinary network design.
Okay, so the error propagation, that has a big impact, of course, and so that does get accounted for in the greedy algorithm. So the constraints that are placed on viewpoints stem from that error propagation. So precision is a function of distance, and it's a function of incidence angle. We can boil it down to that. So we set thresholds for maximum range at which that we want to observe a particular wall, and the incidence angle at which we want to observe. Because say above 65 degrees, for example, then the precision of the distance measurements becomes very poor. So we limit the incidence angle in constructing the weighted greedy algorithm.
Thank you very much. And there is another question from Suni Kushavaha. When the Leica and Pharaoh scanners do not have GPS, how do you suggest precise registration of multi-temporal scans?
Well, again, it depends upon, I suppose, the project. If there's nothing available in terms of control points, then it's probably going to be like an ICP or an iterative closest point type solution. But if there is control points, then you would utilize those. So control points placed in some sort of stable portion of the project. So if it's multi-temporal, then obviously I think that means or implies one is looking for some sort of change. So you need some sort of control that will be immune to that change, or will be invariant over time. And if one is seeking an ICP type solution, then you've got to utilize features or objects that are not changing and over time as well. It boils down to stable control essentially, whether it's signalized targets or other features used in an ICP.
Thank you. And another question, Ernesto Marmolejo Zapata, is a question: scan in motion, that is, place a sensor in a car to detect exterior numbers of each house. That's
okay.
the comment.
Yeah. So is the question?
It's just such a comment. So if you want to say anything too, so.
Oh yeah. Well, I think perhaps the question is like, can we apply these methods, or how do we apply these methods? I would say yes, we could. We haven't gone down that path yet. We've only formulated these methods for the static laser scanning platforms.
So there is not any more question, and yeah. Is there still anybody who would like to ask anything? In between, I would like to ask you, Derek, are you satisfied if we use your recording publicly on the website?
Yeah, that's fine.
Thank you. There. From Suni Kushavaha, again, Professor, does distance from the target, angle, temperature, or target has any effect on the point reflectance, as I have faced issue of noise due to fog when scanning at the early morning hours?
Okay, well, yes, certainly the distance and the incidence angle do affect the precision, and yes, fog certainly does. I mean, atmospheric conditions, and like fog causes the atmosphere to become somewhat opaque, so you can't measure through it.
And he meant also temperature.
Temperature? Yeah, and I'm aware that we haven't looked specifically at, like, there are two aspects to temperature. So we haven't looked specifically at interior temperature of the instrument, but certainly atmospheric conditions will impact the accuracy of the range measurements. But in terrestrial laser scanning, distances are typically close, except if they're working maybe in mine site environments. But I think it's really a matter of applying the relevant correction equations. If you can observe temperature and pressure, then you could in principle correct the observations to account for these effects.
And temperature of target?
Temperature of target? Oh, no, I'm not aware of that. No, I haven't tested that myself. That's interesting though. Yeah, I don't know.
There is still another comment. It's difficult to say. Exterior of the building, reflectance before and after rain. So it's
okay.
Still, yeah, it's still connected to the previous question, I guess, because this is the same question.
Yeah. Well, it probably depends upon the material and how, yes, if the surface is wet instead of dry, then that can change the reflectivity properties, but I can't make a blanket statement as to how exactly it affects, because it's dependent. Like it would be different for concrete than it would be for wood construction or metal or something like this.
There is another question. Why are there different distributions for different scanners after all? Question from Willy Karel from TU Vienna.
Oh, so the different observation distributions. Well, the distribution really depends upon the configuration of targets and the location of the instrument within the target fields. So that's where the differences stem from. It's not instrument dependent per se.
Mm-hmm. And then an anonymous author, does this network design processes will be helpful in planning of photogrammetric observation as well as compared to TLS?
Well, I hope so, but I haven't done that yet.
From Siddhartha Bhuyan, could there be any applications for disasters?
Well, I suppose so, because these are processes for network design, so coming up with configuration that maximizes data quality. And so if for disasters you want to, data qualities are concerned, then you could apply. I don't see why you couldn't apply these processes.
So there is not any other question. We still have 4 minutes. Yeah. Maybe I would like to thank you very much, because I know your very busy agenda gave you just short time for preparation, but it seems that you didn't need it because you are very well experienced in the topic. And I hope that you will continue with your close cooperation with ISPRS, even though you have passed very tough years with being editor-in-chief of the journal, which is really very successful with the impact factor higher than 7, which must be, I think we will have to be thankful for your energy and time you invested to and brought this quality together with other editor-in-chief Chiang Wang together. So thanks a lot. Enjoy the rest of the semester, and let's hope that we'll have good summer for everybody in the world, even though it can be in winter or in summer, we will see. And see you next time.
Thank you very much for your kind words. Thank you. Bye-bye.
Thank you all for taking part in, and we are looking forward to another meeting, which will be at the end of June. And the speaker will be Monica Sester, and we will inform you soon about her topic. So it will be in the last week of June. Thank you all, and have a nice day, evening, night, morning. Bye-bye.